Hello everyone, this is Honors Pre-Calc. This is integration number 2. We're going to talk about what definite integrals are. Now, what a definite integral represents is area under a curve. Okay? I'm going to do my best to kind of explain something that we do in calculus. If you take a curve and you want to define the area from A to B, okay? What we can do is we can take rectangles, and we can use these rectangles to estimate what the area under the curve is. And those rectangles might be a little bit above the curve or a little bit below the curve. But essentially what's happening here, each rectangle, the base is delta x, okay? The height of each rectangle is f of x. Hence the notation f of any x value, and we call it c. C is some particular x value. F of any x value is the height of the rectangle. The change in x at that particular point is the base of the rectangle. I want to add up all those rectangles and I would get something close to the area under the curve. Now, what this notation means is let that change approach 0. So what if all these changes in x approach 0? Then I'd have more and more and more rectangles. And the more rectangles I have, the closer it's going to be to actually estimating the area under the curve. And so this limit, letting the number of intervals approach 0, letting the length of each interval approach 0. In other words, let the number of intervals approach infinity. Add up all those rectangles. That represents the area under the curve, and it also represents what we call the definite integral. The definite integral is when you have two numbers on that integral, and I'm trying to zoom in here. If you have the integral from a to b of f of x dx, that is called a definite integral, okay? The definite integral of f of x from a to b, a is the lower limit, b is the upper limit, okay? Now, if a function is continuous, you're going to be able to find the area under the curve. Now, let me show you something that's a little simpler than some of the stuff we're going to do later. If you were to want the area between the curve 2x and the x-axis here. So here's the graph of 2x. Okay? Here's the area from -2 to 1. Okay? This is the area that's represented, okay, by this integral. Okay? Now, how am I going to find the area of these pieces? Well, the area of this is a triangle. It's 2 times 4. That's 8. And half of 8 is 4. This is 1 times 2 divided by 2. That second area, its area would be 1. But here's the thing. When you're doing integration, the answer here would not be 4 plus 1 and give me 5. Okay? An integral, if the area is below the curve or below the x-axis, it's considered to be a negative area. If the area is above the x-axis, it's considered to be a positive area. So this integral actually equals -3. Okay? There is also a way to do this on your calculator. I'm hoping all of you can see my calculator. I'm going to try and zoom in here a little bit. Let me get it out of the glare there. Okay? What you can do, first of all, is you can put the function into your calculator. Okay? And you can graph it. Again, this is the graph we're looking at on my paper. Now, if you hit second trace, which is our calculate menu, everybody notice number 7 looks like an integral symbol. Okay? Hit number 7, it asks you for the lower limit. Well, the lower limit here is -2. It asks for the upper limit. What's the upper limit? It's 1. It actually graphs the area we're talking about here, and look what the answer is at the bottom of my calculator screen. The answer is -3. The integral from -2 to 1 is equal to -3. It considers that area to be negative. If there's more area shaded below the x-axis than above, the answer is going to be negative. If there's more area shaded above the x-axis than below, the answer is going to be positive. Yes, sometimes if the areas are equal above and below the x-axis, you can get an integral that's 0. Here, let me show you another way to do this. Okay? Hit the math key right here. Look at number 9. It says FNINT. That is function integrate. That is the integral symbol. We're going to go from -2 to 1. I'm going to put in my function, which is 2x. And I got to do it with respect to x. Whoops, I hit my enter key too soon. I got to put an x right there. And look at this. It gives me -3. It gives me my answer. Okay? So there's a couple different ways to do it on your calculator as well. Okay? Now, what we did here is we did it on the calculator and we used areas to find my definite integral. Okay? Now let's go through some properties of definite integrals. Think about this and tell me if it makes sense. The integral from a to a of f of x dx is 0. Well, if you integrate from here to here, you didn't cover any area, so the area is going to be 0. So if you integrate from pi to pi of sine of x dx, it's going to be 0. If you integrated from -2 to 2 of sine of x dx, it would equal 0. Now, if you integrate from a to b of f of x dx, that's the opposite if you integrate from b to a of f of x dx. Okay? And I'm going to pull out my calculator here to prove to you that this works. If you take the integral from 0 to 3 of x plus 2 dx, that's 11.5. Watch. If I do math number 9, and I integrate from 0 to 3 of x plus 2 dx. Sorry, it's 10.5. I must have typoed. Okay? If I decide to change these limits of integration, if I make the top 0 and I make the bottom 3, it's -10.5. Okay? Hopefully you can see that on my calculator there. They're opposites. And let me correct these notes here. This should be a 10.5. Okay? Essentially, if you integrate this way, it's positive. You integrate this way, it's negative. And there's a property we're going to do later that's going to represent why that actually works. Now, if you integrate from A to C, that's this little red area right here. And then if you integrate from C to B, it's this green area right here. Well, wouldn't that equal the entire area from A to B? So if you integrate from 2 to 3, and then from 3 to 6, that should equal the integral from 2 to 6. You're just adding up areas when you're adding integrals like this. Okay? Just like we did before, if you have a function times a constant, you can take the constant times that definite integral. If you add functions, you can add their integrals. Okay? If, what this whole thing says right here, if g of x is always greater than or equal to f of x, then the integral for g of x, which is the area under that curve in the red, should always be greater than or equal to the integral for f of x, which is the area in the blue. Okay? Now, to start off with integration, you can actually do this. Okay? All right? You can actually write or draw areas to represent integrals or integrals to represent areas. We're going to have to be able to do that. So what I did here was I graphed the function 4 minus 2x. This is the graph of 4 minus 2x. Okay? How would I write an integral for that function? Well, the x values go from 0 to 2 of my function 4 minus 2x dx. Now, the other thing is great about this one is you can actually integrate with respect to y as well. Look, the y values go from 0 to 4. Okay? And how would I write this in terms of y? Well, I'd have to add the 2x and subtract the y, and then I would divide by 2. I'd get 2 minus 1/2 y. This function in terms of y is 2 minus 1/2 y. So I could integrate from 0 to 4 of 2 minus 1/2 y dy. The first integral in red gives you that area in terms of x. The second one in blue gives you the integral to represent that area in terms of y. Okay? This function is 1 over x squared plus 1. Here's the area under the curve from -1 to 1. What definite integral represents that area? Well, the integral from -1 to 1 of my function dx. And by the way, sometimes that dx can be written on the top. Dx times 1 is dx. So this is correct also. One more area here. This is y minus 2 squared. Well, since it's in terms of y, let's do everything in terms of y. The y values go from 0 to 2. and it's y minus 2 squared dy. That's the integral that represents this area down here. Now, if I took this function right here and I made it x equals y minus 2 squared, I could take the square root of both sides. Okay? I could add the 2. Okay? And the reason I left this off here, right here, would it be plus or minus? Okay? Well, remember, x equals y minus 2 squared is actually a parabola on its side. Now, in this picture right here, did I keep the positive half of the parabola or did I keep the negative half of the parabola? I kept the negative half. So right here, I didn't put a plus or minus because I want the negative side of that parabola. It's negative radical x plus 2. This function right here is y equals negative radical x plus 2. Guys, remember, radical x goes like this. That's radical x. Negative radical x is flipped over like this function. Okay? So I could integrate from 0 to 4 of negative radical x plus 2 dx. So we can find areas under curves by using integration. I can use geometry, like I did on the first page. I should be able to write integrals for areas that are given. Okay? What else should I be able to do? How am I going to find the integral from negative 1 of 1 minus absolute value of x dx? Well, graph 1 minus the absolute value of x from negative 1 to 1. If I plug in negative 1, I'll get 0. If I plug in 0, I'll get 1. If I plug in 1, I'll get 0. So this is my upside down v, and the area between the curve and the x-axis, that's the area I'm trying to find. Well, ladies and gentlemen, that's a triangle. It's 1/2 the base, which is 2, times the height, which is 1. I can find my integral using area formulas. This is a triangle, so I use the triangle formula to find the area under the curve. You can do that. Same thing here, 2x plus 5. 5 is the y-intercept. You go up 2 over 1, up 2 over 1, but I'm only going to graph this from 0 to 2. So I want the area under that line, in between that line and the x-axis. Now, what type of figure do you see here? Well, ladies and gentlemen, this is a trapezoid. How do you find the area of a trapezoid? Well, it's 1/2 the height of the trapezoid here, which is 2, times the sum of the two bases, which is 5 plus 9. So that ends up being 14. Now, some people will say, well, Mr. Hermiller, I would just do a rectangle and a triangle. You can do that. That's absolutely fine. I used a trapezoid here because it's one of those things that people just don't remember. This picture here, radical 9 minus x squared, that's a semicircle. And it's a semicircle of radius 3. So how do I find the area of a semicircle? I take 1/2 pi r squared. So the area underneath this curve is 9 pi over 2. That's the value of this integral. And you're absolutely allowed to do that when you're working with integration. It's area under the curve. Remember, derivatives are slopes of tangent lines. Antiderivatives, integration is area under the curve when it's a definite integral. Now, if the integral from 0 to 5 of f of x dx equals 10, and the integral from 5 to 7 of f of x dx equals 3, then what's the integral from 0 to 7? Well, from 0 to 5, it's 10, and then from 5 to 7, the rest of the way, it's 3. Just add those two areas. I get 13. What's the integral from 5 to 0 of f of x dx? Well, from 0 to 5, it's 10. So from 5 to 0, you negate it. It's negative 10. Remember, if we switch the limits of integration, it negates the answer. What's the integral from 5 to 5 of f of x dx? Well, if I go from 5 to 5, I didn't cover any area. Okay? From 0 to 5 of 3 f of x dx. Well, it's 3 times 0 to 5 of f of x dx, so it's just 3 times 10. Gives me 30. A few more here. Okay? From 2 to 6 of f of x dx is 10. From 2 to 6 of g of x dx is negative 2. Well, what's f plus g? Well, it's 10 plus negative 2. It gives me 8. What's g minus 3f of x? Well, it's the integral of g minus 3 times the integral of f. So I get negative 32. Pretty simple, right? What's g minus f? Well, that's negative 2 minus 10. That'd give me negative 12. Now this next one I challenged you a little bit. What's the integral from 6 to 2 of 5x plus g of x dx? Well, that's the integral from 6 to 2 of 5x dx plus the integral from 6 to 2 of g of x dx. Now this one over here is easy to do. You just change the limits of integration so it's negative 2 to 6 of g of x dx, and I already know that's negative 2, so it's the opposite of negative 2. That's going to be 2. Now out here, if I change the limits of integration, it's going to be negative 5 from 2 to 6 of x dx. Now, if you were to graph x, everybody knows how to graph x, but I only want the area from 2 to 6. I want the area under that curve, okay? Now, how do you find the area under this curve? Well, there's many ways to do it, but the area under this curve is 1/2 the height of the trapezoid, which is 4, times the sum of the bases, which would be 2, plus 6. X equals 2 there, x equals 6 there. This is a base of 4. Half of 4 is 2. 2 times 8 is 16. So it'd be negative 5 times the integral, which is 16. We found that out by just doing an area of a trapezoid. Then I add the 2, I get negative 78. That's just using my properties for definite integrals. And I hope all of that made sense. Okay? So let's do some practice problems here. Okay? How do you find the integral of the absolute value of 2x minus 4 dx from 1 to 5? Well, I just graphed that function. If you graph this function right here in the darker blue, okay, that's the v that would be formed by that function. I have a first area right there that's a small triangle. I have a second area here that's a larger triangle. Let's just take the area of the two triangles. 1/2, the base is 1 times the height is 2. That gives me an area of 1. That has an area of 1. The second area here has a base of 3 and a height of 6. 1/2, 3 times 6 is 9. The area under the curve is 10. The answer to that integral problem is 10. Okay? Now, take a quick look at these. The integral from 1 to 8 of f of x dx is 13. The integral from 1 to 8 of g of x dx is 7. From 5 to 8 of f of x dx is 5. From 1 to 5 of g of x dx is 4. Now let's figure out a few things here from f of x. If from 1 to 8 it's 13, but from 5 to 8 it's 5, what's the integral from 1 to 5? Well, the integral from 1 to 5 would be 5 plus what would equal 13. So the integral from 1 to 5 of f of x dx is 8. Now let's look at the g of x values. The integral from 1 to 8 of g of x is 7. Well, from 1 to 5 of g of x is only 4. So if I go from 1 to 5, it's 4. 5 to 8, it's got to be how much to add up to 7? It's got to be 3. So let's do some things here. The integral from 1 to 5 of f of x is 8. And I'm going to multiply it by 4. That's how I got the 32. F of x minus g of x from 1 to 8. F of x minus g of x. 13 minus 7 gives me 6. The integral from 1 to 5 of f of x is 8 minus the integral of g of x from 1 to 5, which is 4. 8 minus 4 is 4. From 5 to 8 of g of x, that was 3, minus the integral from 5 to 8 of f of x, which was given to be 5. 3 minus 5 is negative 2. Hope you guys are seeing what we're doing here. The integral from 5 to 8 of g of x we found to be 3. 8 times 3 is 24. Here, from 5 to 1, let's flip it and make it 1 to 5 and put a negative out front. Let's drag that 5 out front too. It's a negative 5 as my constant, and we know the integral from 1 to 5 of f of x dx we found to be 8. So this is negative 5 times 8. Gives me negative 40. Got to be able to use your properties for your integration. Okay. Now take a look at this picture. The integral from 0 to a is 14, right? The integral from 0 to a is 14. Now what's the integral from 0 to b? Well, it'd be 14 not plus 6. That's below the x-axis. That'd be negative 6. It's 14 minus 6. The integral from 0 to b would be 8, because it would be 14 minus the 6. Now what's the integral from 0 all the way to c? Well, it would be 14 minus 6 plus 14. Gives me 22. How about the integral from a to c? From a to b, it's negative 6. From b to c, it'd be 14. So again, it'd be 14 plus the negative 6 gives me 8. What's the integral from c to a? Well, from a to c, it's 14 minus 6, so that would be 8. So the integral from c to a, you flip it, it would put it as negative 8. Okay? And negative 8 times 3 is negative 24. Now, absolute values. If you see an absolute value, the absolute value curve would basically just flip this up and make it positive 6. Okay? Absolute value, no negatives. So if you do this absolute value of f of x from 0 to c, it would be 14 plus 6 plus 14. Gives me 34. Okay? Now, we will get into this more next year, but just a simple use of this. If y equals f of x is a velocity function, the area under the curve represents displacement. So from 0 to a, this object went 14 units to the right. From a to b, it went 6 units to the left. And from b to c, it went 14 units to the right. So when you do the integral from a to c of a velocity function, this is the actual displacement of the particle. But if you do absolute value, this is the actual distance the object traveled. Because distance doesn't involve negatives. He or she went 14 to the right. He or she went 6 to the left. He or she went 14 to the right. That person traveled an entire distance of 34. But their displacement is only 22 units from where they started. So there are some applications for this. Okay, and we'll get into that more next year in calculus. Okay. Now, this page is the nitty-gritty of this particular lesson. It's the first fundamental theorem of calculus. Now, what does it say? If you take the integral from a to b of f of x dx, you take the antiderivative at b minus the antiderivative at a. Now, if I switch those limits of integration, it makes a lot of sense why we change the sign, because then it would be f of a minus f of b. But this is the first fundamental theorem. Now, hopefully you can follow my work here. I can zoom in a little bit here. Now watch what I do on this first problem. This is called a definite integral. The definite integral represents the area under the curve. Okay? Now, if you want to see what this problem looks like, again, I'll try and do this and try not to get a glare on my screen. Okay? If you take the integral, math number 9, and I go from 1 to 2, and I plug in that function x squared minus 3 with respect to x, I know the answer is supposed to be negative 2/3. Okay? You can see that on my calculator. I can also go to y equals, and I can type in x squared minus 3. Okay? And I can graph it. And I could take a look at the integral here. I could go second trace, go to number 7, and I want to know the integral from 1 to 2. You'll notice the area is below the x-axis. That's the area I'm trying to find. But since it's below the x-axis, it's going to be negative. It's going to be negative 2/3. Now, watch how this first fundamental theorem is supposed to work. The antiderivative of x squared is 1/3 x cubed. The antiderivative of minus 3 is 3x. This 1 to 2 is telling me I still need to plug them in. Which number do I plug in first? You plug in the top number first. So I plugged in 2 to both the x's. If I plug in 1 second, I subtract those results. I plug in 2 minus I plug in 1. That's the first fundamental theorem. And if you evaluate all this, you're going to get negative 2/3. Now let's face facts. If you're going to do this entire lesson just by punching them in your calculator, you're not really learning a thing. You want to try this first fundamental theorem to see if it works. Okay? Same thing here. This is 2x to the 1/2. The antiderivative, you'd add 1 to the exponent, and you'd multiply out front by its reciprocal, 2/3. That's how I got the 4/3 x to the 3/2. Plug in 4 first, minus, plug in 1. And next year in calculus, you're going to have to be able to do this without a calculator. The square root of 4 is 2. 2 cubed is 8. 8 times 4 is 32/3. 1 to any power is 1. So it's 32/3 minus 4/3. That gives me 28/3. Okay? And if you don't think that's correct, again, take a look at my calculator here. I could do math number 9. I could integrate from 1 to 4 of 2 radical x dx. And I could even put math number 1 to convert it to a fraction. Look at that. It's 28/3. It works. Okay? What does the graph look like? 2 radical x, graph it. And here's what I want. I want the area of the curve. So let's go down to number 7. From 1, from right there to 4, right there. That area right there is 9 1/3. That's 28/3. That's what we're trying to find with these definite integrals. Okay? Now, what about secant squared? Go to your formula sheet. What's the antiderivative of secant squared? It's tangent. Not tangent of x. This is with respect to theta. It's tangent of theta. Which number do I plug in first? You plug in the pi over 4 first. You plug in the 0 second. Tangent of pi over 4 is 1. Tangent of 0, 0. 1 minus 0 is 1. Okay? This is the first fundamental theorem. You need to know this. We probably won't get into this until like January of next year, but you need to know it. Now again, we talked about this earlier. You do not take the antiderivative of the top and then the antiderivative of the bottom. We do not have a quotient rule for integration. So what you do is you split this up. 16 over x to the 4th minus x squared over x to the 4th would reduce to 1 minus x squared. 1 over x squared. That's 16x to the negative 4 minus x to the negative 2. So this one involves some negative exponents. Add 1 to your exponent. And if you divide by the new exponent, it would give me negative 16/3. Add 1 to the exponent, you would divide by negative 1. There's my antiderivative. Now, which one of these two numbers do I plug in first? I plug in the 8 for x first, minus plug in 1 for x. And you do have calculators, so you could punch this in and get a nice fraction. Okay? Now, we showed you how to do an absolute value before, and we did areas. When you graph 2x minus 4 from 0 to 4, it gives you a v. I could literally do the area of two triangles. That's that triangle and this triangle would actually add up to one big rectangle. 2 times 4 is 8. You can do this problem using geometry. Now, believe it or not, this right here, this is negative 2x plus 4. So from 0 to 2, it's the function negative 2x plus 4. And from 2 to 4, it's 2x minus 4. If I kept going with this function, it would intersect down here at negative 4. So you could do the integral of two different functions. Antiderivative here would be add 1 to the exponent, divide by 2. 4, the antiderivative is 4x. Over here, it's just the opposite. So from 0 to 2, which number do I plug in first? I plug in the 2, minus, I plug in the 0, plus, I plug in the 4 first over here, I plug in the 2 second, and I subtract them. And punch all that in your calculator. You're going to get 8. And you can try that. And again, you could punch this in your calculator and get the answer is 8. But that's really not going to teach you anything except how to use your calculator. And next year in calculus, you're probably not going to have your calculator half the time. Okay? Let's do some practice problems here. And if any of these don't make sense, please let me know. Okay? I hope this is focused. It's hard for me to see with my glasses. Okay? What's the antiderivative of 5x squared? It's 5x cubed over 3. Negative 4x. Add 1 to the exponent, divide by 2. Antiderivative of 4 is 4x. Now, I'm going rather quickly here. You plug in the 5, minus. You plug in the 0. Use your calculators for now. You'll get 535 over 3. Okay? Same thing here. Negative exponent. Add 1 to the exponent. Negative 9/5 plus 5/5 would give me negative 4/5, and you'd multiply out front by the reciprocal. That's my antiderivative. You'd have to plug in 32 minus a negative. It'd be minus negative. That's why this is plus. Minus a negative gives me a plus 5/4. Plug in your 1. Okay? The 5th root of 32 is 2. 2 to the 4th is 16, but the negative puts the 16 on the bottom. 4 times 16 is 64. Here, it just comes out to be 5/4. And in class, we might have to do this without a calculator, okay? So I found common denominators here. I just added them up. I got 75 over 64. You can use your calculator, okay? Ooh, there's that secant squared again. What's the antiderivative of secant squared? It's tangent. So 3 times secant squared, the antiderivative is 3 times tangent. Plug in the pi over 6 first, minus, plug in the 0 second. Top minus bottom. Tangent of pi over 6 is radical 3 over 3. Tangent of 0 is 0. So the 3 times radical 3 over 3, that cancels and gives me radical 3. Once you get good at this, this starts to flow. Tangent squared. What the heck? When I go back to my formula sheet, I don't see tangent squared. I can't use a power rule here because it's not x squared. It's a function squared. That's a big difference. We're going to get into that later. Does anybody remember that 1 plus tangent squared x equals secant squared x? That's a Pythagorean identity we learned. Subtract the 1. Tangent squared x is secant squared x minus 1. That is a Pythagorean identity. Now, why did I do that? Why did I take tangent squared and write it as secant squared minus 1? Because I know the antiderivative of secant squared. It's tangent of x. I know the antiderivative of minus 1. It's minus x. Plug in the pi over 4. Plug in the 0. Tangent of pi over 4 is 1. Minus pi over 4. And tangent of 0, 0. This all drops out over here. There's the value of my antiderivative. That is a problem. You couldn't just punch in your calculator and get an exact answer. It would have to give you a decimal. Okay? Now, this one here, again, I cannot take the antiderivative of a quotient, so I split this up. Y to the 6 over y to the 4th is y squared. 7y squared over y to the 4th is 7y to the negative 2. So I split it apart. Take the antiderivative, add 1 to the exponent, divide by the exponent. Add 1 to the exponent becomes negative 1, divide by negative 1 becomes positive 7 over y. Which number do I plug in first? I plug in the negative 4 first, minus, I plug in the negative 5. I do believe that says 1199 over 60. Double check that with your calculators. Be careful with your parentheses. Okay? Comes out to be 1199 over 60. Now, this next problem's a pain in the butt. Now, obviously, you could do this on your calculator. You could put that in for y sub 1. You could integrate it from negative 5 to 4, and you would get that answer 58.5. Not really teaching you anything. What we would have to do here, if we want to do a definite integral, you'll notice from negative 5 to negative 3, the area is below the x-axis. I have to write an integral for that piece. Plus, the green here, from negative 3 to 0, it's above the x-axis. Okay? All right? And from 0 to 4, it's below the x-axis. Now, this says I want total area. And what did we say about areas? Areas have to be positive. That's why here, when I went from negative 3 to negative 5, or negative 5 to negative 3, I took the opposite of my function. Because if I take the opposite of my function, it's going to flip it up here and make it positive. Okay? I get a positive area for the red. The green part is already positive because it's above the x-axis. Now from 0 to 4, I negated it again. Now this is going to be a pain in the butt to draw. But that area right there, I would flip it above the x-axis and it would become positive if I negate the function. Okay, so when it says find total area, you have to integrate from -5 to 4 of the absolute value of -x squared minus 3x dx, because I want all of the values to be positive. Take the antiderivative, add 1, divide by the exponent. Add 1, divide by the exponent. And what's great about those antiderivatives, they're going to be opposites. This one's positive, this one's negative, this one's positive. For the red, you have to plug in -3 first, minus plug in -5. For the green, you got to plug in 0 first, minus plug in -3. For the blue, you got to plug in 4 first, minus plug in 0. And the reason I cross those out is because the zeros will cancel everything out anyway. Punch it in your calculator. You'll get 58.5. Okay? When it says total area, areas have to be positive. Think absolute values. Okay? One more page here. Let me zoom out a little bit so you can see the whole problem. Hopefully you've printed this out. That will help. A of x is the integral from -2 to x of f of t dt. Capital